All right, gang, STAT1800. The purpose of this video is to introduce you to inference techniques for beta 1. Now, I covered this in the previous video that, we use X bar to make an estimate of mu, and I gave you a variety of examples. In the context of what we're doing here, we use our slope from I call it our sample model, to make an inference or make an estimate, I should say, of the slope for the population model. Now, guys, I found an error, and you guys probably were screaming at me at the top of your lungs. A few videos back, I was showing you how to find, well, I forget what I was, no, I take that back. Forget that. I was showing you how to find the standard error of the estimates. And most of you may be sitting there thinking, yep, Dr. Darbro, I saw you mess up. Okay, well, you probably did. You're probably screaming at me, no. All right, anyway, I told you that the formula for this was to take the sum of squares for the error divided by n minus 2. And here's the way I illustrated it. I illustrated it by saying, well, our sum of squares for the error was 8.643. And our sample size was 3, and 3 minus 2 is 3. Well, guys, trust me, I know 3 minus 2 is not 3. I just got sloppy. That should be 8.643 divided by 1. So that changes our standard error of the estimate to taking the square root of 8.643 to be 2.940, actually. All right. So I noticed that when I was preparing for this video that the numbers that I were using were coming out correctly, and I couldn't understand why, and then I went back and looked. So instead of redoing the video completely, it's not that big of a deal because we haven't had to use this in anything previous to this video, but we are going to use it in this video. So guys, make a note in your notes that I created a boo-boo right there. All right, much more importantly, what does the inference procedure for beta 1 look like? Well, as you would expect, it starts out with a statement about the null hypothesis. And we assume that the slope of the regression model is equal to 0 unless there's, guys, I am messing up big time. It should be B1. That the slope of the regression, all right, can't stand that. It's not going to work. That the slope of the regression model is equal to 0 unless we find evidence otherwise. Now, let me explain to you what that means. If we have a relationship between x and y where there's no linear relationship, what we would have is we would just have scattered dots like this. The line of best fit for this would be a horizontal line which would have a slope equal to 0. We want to see if there's evidence to indicate that the slope is something other than 0. Maybe it's positive. Maybe it's negative. In other words, something other than 0. So we just assume that the relationship between, this is for the population X and population Y, that the relationship between is nonlinear. And then we go out and get sample data and look at our sample data to see if it indicates that we should reject this statement based on the evidence that we collected and conclude that the slope of the model is not equal to 0. So guys, as you would expect, the first thing we do, other than setting the null hypothesis and the alternative hypothesis, is to set our alpha value. The next thing we do is we set our test statistic. And guys, it turns out our test statistic in this type of problem is a t-statistic. So the t-distribution, again, defines the distribution we use to find the p-value and the critical values. And the numerator is pretty much as you would expect, because if you think back to when we did these problems with mean, we had x bar minus mu. When we did these problems with proportions, we had p minus pi. When we did these for the difference of sample means, we did x bar 1 minus x bar 2 minus mu 1 minus mu 2. And then we have the standard error for beta 1. Now, this is where things get a little crazy, because the standard error for B1 is equal to the standard error of the estimate divided by the square root of the sum of squares for x. And guys, just in case you don't want to look back in your notes, remember that, as I just showed you, s sub yx is equal to the square root of the sum of squares for the error over n minus 2. And ssx is the sum from I equal 1 to n of our x values minus the mean. All that's squared. So guys, our test statistic is going to be pretty easy to find. All we have to do is we have to find B1, and we'll do that using StatCrunch. Well, guys, we've already done it. We already saw in previous examples that the B1, and guys, I'm using the data set, what was it, 1, 3, 7, 2, 10, 15. And this was the slope that we found when we ran StatCrunch on that before. So guys, the test statistic will be 2.036 minus 0. Our SB1, I just found earlier, was 2.940. And our SSX was 18.667. You can look back in a previous video and you can see where I calculated that in a previous video. All right, so you got to be careful putting this in your calculator, otherwise things can go wacky on you. So let's go 2.036 and divided by. So we have to put the numerator by itself in the denominator in parentheses. So 2.940 divided by the square root of 18.6667. So guys, we get a test statistic of 2.99. To calculate our p-value, we're dealing with the t-distribution. Degrees of freedom equal n minus 2. So we have a t-distribution of 1. And we need to find the area to the right of 2.99 and to the left of negative 2.99. So guys, our upper area is 0.103, and our bottom area is 0.103. So guys, going back to our total area would be 0.103 times 2. So our p-value would be 0.206. Guys, as you might imagine, we can do all that using StatCrunch. I just want you to know, where these numbers come from. So simple linear, we're going to use variable 1 to predict variable 2. Now the hypothesis test does the intercept and the slope, so we kind of get more bang for our buck than what we maybe set out to do, because all I really wanted to do here was to illustrate the slope. But nevertheless, you can see that now we did all the analysis, the ANOVA table before, so you should know where every one of these numbers come from. But you can see now in the slope, you can see that our estimate is 2.0357. That's our B1. Our standard error is everything in the denominator of our test statistic. We have our alternative. We have our degrees of freedom. You can see that our test statistic is 2.99 as we calculated. And our p-value, I have 0.206. This is 0.2054. Again, it uses the entire number in its calculation. I only used 2.99, so we're off a little bit, but still, the p-value is greater than 0.05. So guys, you have 3 ways to evaluate whether a statistically significant relationship exists between X and Y. And what are they? The ANOVA, which gave you a p-value of 0.205. Rho, R, which gave you a p-value of 0.2054. Remember that? If you don't, let's do it. We can go summary stat. We can go correlation. We can choose both of these. Two-sided p-value. Look familiar? And we can go inference on our slope. Now again, the reason that we're not getting statistical significance here, because if you can go on over and look at the relationship, I mean, it's a linear relationship, but we just don't have enough power to reject the null hypothesis when it's actually false, because we only have 3 measurements. So in reality, what we would want to do is bump up our measurements. Now, let's run through an example. Guys, data set from your textbook, if you go to simple linear regression, one that I found that was semi-interesting is called Redwood. And what I found interesting about Redwood is I was in California not long ago, and up in Northern California, these redwoods are absolutely amazing. I mean, these things sometimes go to heights of around 300 feet, and you wonder how in the world can they measure the height of a tree that's that high, and of course you could use trigonometry and stuff, but statistically there's another way. And what studies have shown, and what we want to kind of test here, is that the diameter of the tree at breast height is a good predictor of the height of a tree. So what they did is they went out and collected a sample. Now, again, what are they trying to generalize to here? They're trying to generalize to all redwood trees. Can they predict the height of any redwood tree based on the diameter at the breast height? So they have measurements on 21 trees, and they want to create, well, we want to create a model to see if the diameter is a good predictor of the height. So guys, the first thing I would probably want to do is just look at the correlation between diameter and height. I'd want to look at a two-sided p-value. I would compute and I would see that I get statistical significance. My correlation coefficient is actually lower than it was in the previous value. I think it was 0.96 or something before, but we didn't have enough sample size to create enough power to reject the false null. But now we have statistical significance indicating what to us? Indicating that the breast height and height have a significant linear relationship. Well, let's dig a little deeper. Let's go look at a scatter plot. The x variable, I want the diameter of the breast height. The y variable, I want the height. I don't want any of the fancy stuff yet. And let's compute. And you can see that I do have a linear tendency. In fact, as the diameter of the breast height gets higher, gets bigger, the predicted value of the tree is going to get larger. All right, let's move into regression. So we want diameter of breast height to predict the height of the tree. I want to perform a hypothesis test. And I want to save the residuals. Now I'm looking at two things, but notice they give me the same thing. My slope is statistically significant, indicating again that the relationship between diameter at breast height and the height of the tree is statistically significant. I can come down to my ANOVA table, and you can see that overall, predicting the height of the redwood can be significantly predicted by the diameter at breast height. Now, are our assumptions violated? Well, I've saved the residuals, so I would want to go in and look at a residual plot. So I go to a scatter plot. I want my x value to be my original x, but I want my y value to be the residuals. We talked about this before. Now, what are we looking for? If we see kind of a shotgun blast, no pattern, then we have no reason to suspect that we've violated normality, equal variances, independence, or I forget what the other, well, I gave it to you. Normality, independence, linearity, and equal variances, yeah. So guys, I see a little, maybe a slight pattern, but guys, that's shotgun-ish blast. I don't know, that's not even a word, but that's close enough to kind of a shotgun blast. Randomness, no patterns, no discernible patterns, for me to feel fine that I haven't violated any of the assumptions for conducting a linear regression. So guys, it looks like to me that if I can go up and stand beside of a beside of a redwood, and at my breast height, if I can measure that tree to be 30 inches, for example. So 30 inches, for example. I can come down and put in 30 as my x value, and I can get a prediction on that. So a tree that has breast diameter of 30 inches would be predicted to have a height of 158.99 feet. Now, the confidence interval would range somewhere from the prediction confidence interval. We haven't got into that yet. I'll get into that probably next week. Honestly, I think I've thrown enough stuff at you for now, but really, I don't know. I may end up going ahead and putting up another video, so we'll see how it goes. So guys, that's that's about all I have for you in this video. So more to come.